I hope you can all see my screen there. And I'm going to crack straight on. I've only just come back from holidays. I've had a month off with my 11-year-old. So we were staying at Bells Beach, which is the picture behind me. And we watched a lot of Scooby-Doo cartoons, which are going to feature because I had to do some of this while on holidays with my son. But how cool would it be if you're a bit of a geeky nerd number person like me, if you opened up your TV guide and saw a show that was all about the mysteries involved in doing analyses. Today I'm going to talk you through one of the mysteries that we had recently, and we're going to run through just some of the plots that I used to help get around what happened. And we did end up solving the problem, and I've accidentally missed that line at the bottom of the slide just to make you wait for 20 minutes to hear how it finished up. But one of the areas I work in is interrupted time series in public health. And a bit like the difference in difference we were looking at before, we often have data that we can't do a proper experiment on. We can't do a randomized controlled trial. We need to do something else. And these interruptions can be policy implementations, natural disasters, anything that you want there. Now, one of the methods that we use involves collecting data over time. Here's an example using just some infection data. And what we want to do is see whether we can determine what the impact of that interruption was. Now, we've got several characters in our regression formula here. We start off with our y-intercept, that's our beta 0. And then we can move on to looking at beta 1, which is our pre-interruption slope. So we want to take into account whether infections were already rising before something came in or whether they were decreasing. And we can do that. And this is kind of like when you're watching Scooby-Doo episodes, you see the butler and you know the butler did it. And you reckon by the end of the episode, you know exactly what's going to happen. And that's how we sort of use that data. We make a counterfactual trend line. And then, of course, partway through, something happens. Maybe the butler dies and then he can't be responsible anymore. But there's a jump scare or something happens. And in the parlance of these segmented linear regression analyses, we refer to that as the immediate level change. So there's a sudden shock to the system. Now, obviously, that can be positive or negative, but we can try and measure that. Another thing that we can measure is whether there was any actual change in the slope afterwards. If you really want to reduce something, you kind of want to keep it reduced, and therefore you might want the slope to at least be the same as it was before or even decreased. Now, by looking at the level change and the slope change, we can get a good idea for whether there was an actual impact of that interruption. Now, being time series data, we can't just assume that our points are totally independent of each other, and we do need to include some sort of autocorrelation. The example I'm using here is just a lag 1 autocorrelation, and that's going to group points together. Obviously, if we're looking at infection data, the infections on a Wednesday are going to very strongly relate to what they were on a Tuesday, which will strongly relate to what they were on a Monday, etc. Now, I must admit, this is the one time I cheated, and I did use R just to do this animation because it's got a nice smooth animation package, but everything else is in Stata. And I know we talked before to Chuck about different graphics things. So anyway, let's crack on. We did a whole heap of research about which statistical methods researchers can use to look at interrupted time series data. Often with the public health, we've got really sparse data. And so you might have no deaths for a few days, and then you get 1 or 2 and then none. And some of the statistical methods don't work well under those situations. So researchers aggregate their data. And in the research we were sharing with them, we were saying you want to try and have as many data points as possible, but obviously when you aggregate, you'll lose some data points. And so they were saying, well, what do we do? Is there a preferred option? And we said, I don't know, let's find out. We looked at the most common aggregations that the public health researchers use: weekly, monthly, quarterly, and yearly. Now, here's an example from the literature, just to show you the sorts of graphs that they tend to use and the types of wording that they use. This is straight from the abstract of this paper. And it says there was an immediate 26% decrease. That's our level change. And then it talks a little bit about a 6% reduction, and that's the slope change. So these are all, no matter what they're looking at, very similarly worded, and you'll see many graphs that all look very similar as well. Here is the smoke-free legislation in the UK. across different districts there. And again, 4.3% reduction, that was the immediate reduction, and an additional 1.5% per annum working on. So we've got this level immediate and a longer term slope, but there's lots of different ways we can aggregate that data. And so the researchers were saying, if I've got lots of daily data, is there a best solution, or are there some characteristics to look out for? Now, the first thing I did when I was asked that question was said, yeah, let's do a simulation and work that out. Now, I love doing simulations. Anyone I work with just sort of dangles that in front of me because they tend not to, and I'll jump right in there. If you're unfamiliar with Scooby-Doo, he's the dog, and he'll do anything for a Scooby snack. And for me, that's running a simulation. Now, I use Stata. I love how reproducible it is. Right from the get-go, you can generate your data, you can analyze your data, you can do your graphs and your tables. And just like Joe was talking about before, I think that's really important, and lots of journals are requiring that now. The most recent journal I submitted to actually required that not only do we submit the code, but they have to be able to hit run and generate everything, all the graphs, tables, and the works. So I think that's really important, and Stata makes that really easy. So let's simulate some data. Something else that I like about Stata is how easy it is to do this. Now, I use the Tim Morris's ADEMP method. We use in public health a lot for simulation studies, and I thought we'd just run through a little bit of what that looks like. But here we've got the formula we saw before, and I'm going to generate 12 years of data, 6 years before the interruption, 6 years afterwards. And in Stata, I just said, can you please just give me consecutive dates starting from January 2020 all the way through to end of December 2031. Bang, done. I then used the formulas from before, and we used a whole heap of different parameters and generated outcome data. And when it comes time to analyze that, again, really nice and straightforward. First of all, we just have a time variable. Dates are messy. No one particularly likes working with dates. So again, I'm sure we're all familiar with Stata, just being able to go gen time equals underscore lowercase n, that's sorted. So that's easy. Now, just like the models that we were looking at earlier on with Jeff, we often just have these indicator variables, and there's no difference here. Our immediate level change, that's our drop, is just set to 0 before the interruption, 1 afterwards. And in this case, we want to track the slope as well. So it's very similar to the level change. It's just 0 before, and then we just increment up afterwards. So really straightforward. Run that regression model and get your parameter values dead easy. What about when we aggregate? Well, again, when we look at what the best ways are to aggregate and what researchers are doing, then we can just do exactly what we were doing before with one tiny change. Here's a graph showing the data that I showed you before. All the tiny little gray dots are all the daily data for those 12 years. And all we need to do is find the average. So again, Stata can do that in a flash. That's our orange diamonds there. And when I see that in a table, easy. We just got 12 years. We've got the average outcome within each year.
What was wrong?
Now we can analyze that in exactly the same way as we analyze.
It was okay.
Did you get any comments?
Oh, a couple, but mostly
Mostly
John Deneau.
There we go. We've got our level change, again, 0 before, first 6 years, nothing, then 1 afterwards, and slope change as well. So even though one of these is aggregated data and one of them isn't, it's super easy to code because Stata doesn't care and my do file doesn't care. So I have a separate do file. So when Joe was talking about different chunks of code, I'll have a separate do file that's got the analysis code, and I just feed in whichever part of the simulation I'm up to, and it works a treat. Now, before I show you the results of which statistical methods work best, I just always take the time to run through and check that my data has been generated correctly. So let's just do a quick test here. My model input was a level change of 2, that's beta 2, a slope change of 0.002, that's beta 3, and an autocorrelation of 0.4. And the graph comes up and it looks just right. We've got autocorrelation estimation, the same, perfect, level change of 2, and then we've got our slope change. Now I'm just going to check that for our aggregation. Here's our weekly data. It's got slightly less variation, which is actually what we want. That means it's working fine. We're aggregating a week's worth of variation into 7 days. And our autocorrelation has dropped because we're not looking at single time lags anymore. We're looking at averages over 7 days. And we can look at monthly and we see the same trend. So this looks like it's working great. Scooby-Doo is giving us the thumbs up. The level change is the same in all of them. The slope change is the same in all of them. I've done a good check there. Obviously, in real life, I do this lots of times. I'm not going to show them all to you because that would be boring very quickly. Now, when we simulate, we're simulating millions of these, and then we want to double check that they're working. Now, we could sit through and look through millions of individual graphs, but obviously, we're not going to do that. So let's have a look at one of the graphs that I use for checking things like the variance. Now, here's a Stata graph where I've used a bar graph. I've actually used a double bar graph. Firstly, I'm looking at our aggregation, daily, weekly, monthly, quarterly, and yearly. And then within each of those aggregations, I'm looking at our 3 different level change parameters we chose to look at, 0, 1, and 2. And then I've done the bar graph on those. And within each of those, I'm looking at the 3 different slope change parameters we looked at. Now, why am I doing this? Well, I want to just double check that all of my simulations are working at a glance. Each of these dots represents the results of 10,000 simulations for that particular set of parameters. And I can see very quickly the pattern that comes out here in that the variance is quite high for daily data and drops all the way down to be quite low for the annual data, which is exactly what we expect. We also would expect that there's no change depending on the level change or the slope change, because that doesn't impact the variance of the data. So this is looking good. So Scooby-Doo is going to give me a thumbs up for that one as well. Another type of graph that I like to look at are these. I've just dropped down the bottom here. What these are now I'm looking at all of the level change estimates for a parameter combination. And I want to see that I could look at just a scatter plot and see that they're coming out mostly to the value of 2, which is the value we expect them to be. And that would be okay. But I'm also interested in the spread of those estimates. And that's because we've got some random variation. It's not always going to come out at 2. There's going to be a bit either side. And what I want to see is a nice kind of normal distribution there. And this looks good. Now, I've also done here 2 different colors. And that's just because we looked at about 7 different statistical methods. I'm just showing 2 of them here. And in this case, I expect them to look the same, and they do. So I'm very happy with that. Now, that was when there's no slope change and 2 for the level change. I can just quickly check that these look all the same, even when I'm looking at different parameter values, and they do. So that's good. I don't expect my level change estimates to change based on the aggregation or on the slope change. So these all line up really nice and neatly. Perfect. These are looking good, monthly, quarterly, yearly. Scooby's going to give me the thumbs up. Oh, hang on a second. No, he's not. Something's gone funny here. What's happening up in the top corner? These distributions should be giving me a level change of 2, but they're not. They're all shifted across. Now, this was our shocking twist. There's a bias in the immediate level change. When I first saw this, my natural assumption was, I copied and pasted this code from my previous project and I did something wrong. But I double checked the code was fine. We looked at the tables of numbers, that was fine. I need to work out what's happening here. So what did I do? Well, I'm a very visual person, so I made more graphs. One of the graphs I wanted to do is to have a look at all the different parameter combinations and see whether I just happened to pick the one where this happened or whether this was something a bit more systemic. So here's what's called a nested loop plot, and this is showing lots of data. It's like a bird's eye view of all my parameter combinations. Each little dot here is the average level change bias for 10,000 simulated data sets, and each dot represents a different combination of parameters. We had autocorrelation, variance, statistical methods, slope changes, and level changes. And so each of these dots is showing me a different average for each of those different possible combinations. I think there's about 360 different combinations there. Now, what I can do with this bird's eye view is have a good look and see if there's any patterns. And I can straight away see, yeah, there's something big happening up here in my yearly data that's not happening at all in my daily data. So that gives me somewhere to start. So let's have a look at the yearly data and break this down a bit. Now I've got all those different things. I've got autocorrelation and variance, etc. What I want to do is see if there's any patterns that emerge when I look at each of those one at a time. And again, I can do that very easily because in Stata, all I'm doing now is I'm coloring the dots differently depending on what they are. So I've got blue dots for 0 autocorrelation, orange dots for 0.4 autocorrelation. And if there was some link between autocorrelation and this bias, I'd see all the orange dots in one spot and all the blue dots somewhere else, but I don't see any pattern here. They're all very similar to each other. And I can just repeat that process for my different combinations here. Here's my variance. Again, the blue and orange dots are all right next to each other, so there's no pattern to be seen there. What about my statistical method? No, both statistical methods are showing the same thing. What about slope change? Oh, hang on, here we go. Now we've seen something interesting. These blue highlighted ones are all our 0 slope change, and they're all down at 0 level change bias. Green ones, on the other hand, they're all up the top. So they've all got high bias, and these ones are all, if I follow this down to my little zigzag here, they're all my 0.002 slope change. And then the orange ones are right in between. So looks like slope change is a culprit here. What about level change itself? No, and this one surprised me when I first saw it, because I kind of thought if you've got a large value of level change, which is these green ones over here, it might have a larger bias than when there was no level change. But no, it looks like that's independent. So you can rule that out as a factor. And finally, in our bird's eye view, we could quite clearly see a pattern here too. We've got more bias when we've got more aggregation. So that's our bird's eye view. We've identified that slope change and aggregation might be our main culprits. But now I want to see, is this just something that happens for some reason when I'm accumulating all this data, or can I see it when I look at it as an individual study? So now we've gone from the bird to the worm. Here's our worm's eye view. Now I'm looking at a level change that was simulated to be 0. And here's my pre-data here, all looking nice, lots and lots of daily dots here. Post data, lots and lots of daily dots here. And where they meet, no level change, so no bias, so that looks okay. So what's happening with yearly data then? Here's my yearly data. I've only got my 12 data points now, but I can clearly see that there is something happening here. All of these points appear to be shifted upwards. Now that's weird. At least I thought it was weird. What are we going to do? Well, I've got an excellent team, and so we sat down and I'm just sharing with you a couple of graphs. They had to sit through about a bazillion graphs. So I just went graph, 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 graph. And we all just had spitball ideas on what we thought should be happening here. Now, the level bias is related to the slope and aggregation, but slope shouldn't be related to the level. There's no link between the parameters at all, or in my regression model. So I don't know what's happening there. It's not even about the size of the level change. There's bias even when there's no level change. It is how you calculate immediate level change. We all came from slightly different backgrounds and use slightly different code, but no matter what code we use, including the code that we took when people reported their code, we still got the same thing. Then one of my colleagues said, can you just go step by step slowly and let's just go one thing at a time. And they pointed out that I actually wrote something once that I wasn't doing. We wrote a paper on how to create effective interrupted time series graphs, based partly actually on what I've seen in these lectures over past years. So that's been really helpful. And there's this line: considering our purpose, the following components should be displayed. Number 2 there is show the interruption time. And my response was, I am showing the interruption time. Here it is right here. 6 pre, 6 post, here's our interruption time. There's still bias. I can generate my counterfactual and I can see the difference, and that's the definition of immediate level change. But this colleague persisted and said, no, I'm not across the code, but what you've shown me there is the analysis part. What were the actual timestamps on it? And that's when I had to go, oh yeah, we made model assumptions right at the beginning and got rid of time because it's a bit awkward, and went with numbers. I should really put that back the way it properly is. And when I do that, here I've just put behind it the daily data that made up that annual data to begin with, and reminded myself that the actual time of the interruption was in January, but because we'd aggregated in a year, the actual data point is sitting there in July. So that word everybody keeps using, immediate level change, I do not think it means what I think it means. Because actually, when you aggregate, immediate no longer has the exact same definition that you might be expecting when you're talking about daily data than yearly data. In this case, our immediate is actually 6 months after the interruption time. So Scooby-Doo is going to do a quick fix here because it's very easy and very straightforward to make these adjustments. Here I've just created two brand new statistical methods that are very, my son said that was very boring because I called them the halfway adjustment because we're looking halfway back in time. Maybe someone can come up with a better name. Here's our original two graphs, the red and the blue ones, showing the bias. Here's our new and improved ones, back where they should be. Now they look the same as all the other ones. So that's perfect. And we've done it. We've solved the bias, and it's quite straightforward, really, because these halfway statistical methods are super straightforward. You can calculate the immediate level change, the true immediate level change, just by extrapolating back a bit. And in Stata, you just use the lincom command. You run your fancy regression, and then you just lincom back half an analysis time point, and it even gives you confidence intervals. There are a couple of other stats packages that can give you the amount, but they don't always give you the confidence intervals, whereas Stata's lincom command does. So that's excellent. And of course, something else you can do is just be more accurate. So when we're reading interrupted time series papers now, now we need to know that when they use the word immediate, it doesn't always mean immediate. Often it's a shorthand because that's how you analyze it using that code, but actually it could mean that you're out by 6 months, or maybe you should more correctly say the average change the year following the interruption, or whatever your actual timing is. So in typical Scooby-Doo fashion, they normally take off the mask and tell you who was the culprit. And in this case, it's being too engrossed in the mathematical model, not being precise in the graphing, and using inaccurate terminology all along. I mean, we should have known, and they would have got away with it too. So, you know, we've got Scooby-Doo, there's 80s cartoons, so there's always a moral at the end of the episode. The moral this time was try not to get stuck in the model so much. I was so focused on my stats model that I forgot that there's a couple of shortcuts we made that maybe caused some inaccuracies. Plenty of assumptions being made that we talked about earlier before with difference in difference models, and sometimes we forget to incorporate them when we're describing how accurate our results are. I like to graph things as much as possible because I'm a very, very visual learner. So I like those really abstract summaries where you're looking for patterns, and I like then going back and looking at just the raw data to see what it means. Accurate terminology is always important, and having meetings, fantastic. Probably would have taken me a lot longer to work out what was going on if we hadn't had people bouncing back and forth and me having to explain myself. And so conferences like this are great too. And be careful next time you're reading an interrupted time series research paper. If you see the word immediate level change, just have in the back of your mind that immediate may not mean what you think it means. Anyway, I know I'm just about out of time here. And you may have noticed that actually, if you're in charge of my investigation, you might actually be saying, what about the actual question? What are we supposed to aggregate to? And I'm afraid it took me so long to work out why there was this bias that we haven't quite published the next step yet, but it's on the way. So stay in touch, but I'm going to have to leave you on a cliffhanger at the moment, I'm afraid. Anyway, I just want to say thanks to my research team and to all you folks for listening, and to Stata for making my job even vaguely feasible. If we don't have time for all of your questions, then feel free to email me or check the research that's coming out from me and my team at a later date. Anyway, thank you, and I'm very happy to have any questions if we've got time left for questions.
Yep, Simon, we've got one question here from Jimmy. Would it matter if the pre and post periods were not the same length?
Yeah, that's a great question. And the answer is there are some slight differences in the standard errors that you get, but it actually doesn't make a difference to any of the other parameters, except obviously to say that it does matter what the actual aggregation level is and how much slope there is. If there's no slope, you're not in any trouble. It's only when there is a slope. But you can have a short pre and a long post, or vice versa. You'll get the same problem if you're doing this aggregation. And in terms of just normal interrupted time series, you'll just get slightly off standard errors if you don't have matched, but it's not a very big deal.